Hello everyone, I'm Shukri Odhikari. So today will be, so this is the first live session for Discrete Mathematics course, and I'm a PMRF student from IIT Kanpur. So you all can see my screen, right? Please verify that. Hello? Can anyone please verify if you can hearing me or seeing my screen?
Yes, your screen is visible.
Okay, thank you. Okay, so we will start with some problems. Or if you have any problems for yourself, then you can also share it with me. So let's start with problem 1. So there are two propositions P and Q are given here. So the proposition P is that you drive over 65 miles per hour, and the proposition Q is that you got a speed. And all you have to do is that we have to write these statements over here as a logic with this proposition P and Q logic. So let's try that. First one is that you do not drive over 65 kilometers per hour, 65 miles per hour. So this drive 65 miles per hour, this was the proposition over here. But the statement was here says that you do not drive over 65 miles per hour. So that means this can be written as this negation of. And the statement B says that you will get a speeding ticket if you drive over 65 miles per hour. So it is a compound statement. So this statement we have, you will get a speeding ticket. So this is the proposition Q. And you drive over 65 miles per hour. This is the proposition. Now over here, as you can see, that it says that only when it says that if you drive 65 miles per hour. So if this proposition P is true, then only you can say that Q is proposition. So this is nothing but the implication P lies. In the third statement, we have you again. This is nothing but the proposition P. And it says that you drive over 65 miles per hour only if you will get a speeding ticket. I would say that only when Q is true, then only you can say that P is true. So which is the necessary condition for P. So whenever Q is happening, then only P is happening. So Q is a necessary condition for P. So we can write it like Q is a necessary for P. So that means that whenever Q happens, you can say that P also happens. Or whenever P is true, you can say that Q is also true. But if P is false, then can you say that Q is also false? Well, you cannot say that. You can also either be true or false. That's why Q is a necessary condition for B, not the other way around. So over here, we can again say that this is implied. Value have driving 60 miles giving over 5 sufficient for now if the is say that Q so this is again this is the implies. This is how we can write this using the this logical connection. So let's go to the problem 2. So we have two of these statements. So we can figure out what the inverse corresponding to this thing. We have something like this. P implies Q. So what is converse, contrapositive, and inverse statements. So the converse is nothing but Q implies P. So if P implies Q is over here, then the converse of this of this statement is Q, and that means that negation of Q implies and inverse is negation of P implies negation of. So given this two statements, we have to figure out what is the converse statement, contrapositive statement, and the inverse. So first of all, we have this statement. We have the statement that if it's snow, then I will go to ski tomorrow. So if it snows, so it's snow today. This is our position P, and I will go to ski tomorrow. This is our position P. So if it snows today, then I will go to ski. Then this is the statement A over P implies. So the converse statement Q implies P. So that should be if I will ski tomorrow. If I will go to ski tomorrow. Then it's not. So this should be the converse statement of statement A of. Okay. So what should be the contrapositive statement? So the contrapositive statement is basically not Q implies not P. Oh, sorry, not this. We are right. Not. Not. So what is the negation of this statement Q? Q is the negation of this statement Q is that I will not go to ski tomorrow. So I will not go to ski tomorrow. And what is the negation of this statement over here? It snows today, so it doesn't snow. Okay. So the contrapositive statement should be if I will not go to ski tomorrow, then it doesn't snow. So this should be the contrapositive statement. Okay. Next we have the inverse of this statement. So the inverse statement was that not implies. So what is the negation of this statement P? It is it does not snow. And negation of this statement is that I will not skip component. Okay. So this not a negation P implies negation Q. It should be, if it doesn't notate, then I will not. So these are the three statements that we have here: the contrapositive and inverse. Similarly, we can do this for this one. Positive integer is a prime only if it has no divisor other than 1 and x. So over here, we can assume that a positive integer is a prime. So being a prime is a prime. This statement, we can consider it this as the proposition B, and it has no divisor other than 1 and itself. We can consider this as Q. Again, our statement should be P implies Q. Then the converse should be Q implies P, which is nothing but if a positive integer has no divisors other than 1 and itself, then it is a prime number. So that should be our converse statement corresponding to this statement. Again, the contrapositive statement, Q implies not implies negation Q implies negation P. So the negation of this integer has one divisor. Can say it is not a prime. That should be a contrapositive. And implies negation Q. So what is the negation of P? That a positive integer is not prime. And this statement should imply that a positive integer is not prime. If a positive integer is not prime, then it has at least one divisor other than 1 in itself. So that should be our final statement. Okay. So now we have seen how to construct this converse, contrapositive, and inverse statements. So get to this problem. So we have to construct truth table for this compound proposition. So we have this propositions over here, and we have to find the truth table corresponding. So there are two propositions basically, P and in both of these cases. So let's try this first case, which is P implies Q. Junction application P implies. Sorry, application only Q. Okay. So let's find out the truth table for this. So P and Q are the propositions. Again, negation P and negation Q, we also have to find those. And given P, Q, and all this, we have to find first this one. We will also find the truth table for this. And finally, let's name it as X. Final X. Okay, so this can have two possible values, either true or false, and Q can also have two possible values. True. So this pair may have four possible values, either true, 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 false, false, true, or false, false. And if P is true, the negation of P, that should be false. False. And corresponding to every false assignment of P, it should be true. Similarly, for negation of Q. Now we have to find the truth table for P implies Q. Now P implies Q over here. So as you can see, if P is true and Q is false, then P implies Q, that should also be false. Because if P is true, P was the sufficient condition for Q. So if P happens, then Q, or if P is true, then Q should also be true. But this is not the case over here. Oh, sorry. P and Q. This is indeed the case over here, since P is true and Q is also true. So P implies Q. Similarly, so as I was saying before, so P is over here is true and Q is false. So this cannot happen, because if P is true, then Q should also be true, since P is the sufficient condition for Q. Therefore, this should be false. Now, whenever P is false, it doesn't matter whether Q is true or false, because since P is not true, therefore any assignment of Q that should give us P implies Q as. Over here we have to find this negation of P implies Q. So here is negation of P and here is Q. So first one is for if implies Q. So this cannot happen. If this is if the hypothesis is false. Oh, sorry. If the hypothesis is false, then the conclusion can be true. So this is for the first. If the second case, false implies false, this is also true, because both hypothesis and the conclusion, they are both of them are false over here. And therefore, this is also true. The third case is true. The hypothesis is true and the conclusion is also true. So that case also be true. But in the final case, the hypothesis over here is true, but the conclusion is false. So that cannot happen, because this over here, not P is the sufficient condition for Q, and therefore this should be false. So finally, we have to just do the conjunction of these two statements over here. So the conjunction of both true, that is again true. Conjunction of false and true, that should be false. Conjunction of true and true, that should be true. And finally, conjunction of true and false, that should be false. So the truth table for this over here, this compound proposition over here, this should be this. Now, similarly, we can do this for this proposition over here. So let's say that now my X is not P, negation of P by implication, negation of Q. That has again by implication P by implication Q. Okay, so again P, Q, negation P and negation Q. So there are 4 possible assignments for PQ. And for each truth assignment of P, we give the values to negation P. And over here also false true, false true. Okay, so now we have to find this. Now we know the pi implication statement. That means that so pi implication is basically if only statement. So whenever P is so this so basically this means P by implication Q. So this means that P is true if and only if Q is true. So that means if both P and Q have the truth assignment T and T, then we can say that this can have the true. On the other hand, if they both have the value false and false, then we can also say that this is true. This proposition is true. But if they have true false or false true, then for both of these cases, this will be this will have the value of the false. Okay, so for negation of P and negation of Q, we can see that for the first case we have the truth assignment P, and also for both of these uh, for if both of them have truth assignment T, then we can also have truth assignment T. But for rest of the cases, they should be false. Again, for P application Q, we have for the first case we have true. For second and third case, we would have false. And for the final case, since both of them are false, then it should be true. And finally, we have this over here, and by implication of this, which is X. So now we have to take care of this X. Now, as we can see, for both of the cases, for all of the rows, we have T, T, F, 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 and T, T. That means in all of these rows, both of the truth assignments are same for these two propositions. Therefore, X should be true, 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 true. So it doesn't matter what is the truth assignment to P and Q. The X is always true. So what do we call X over here? So this is nothing but tautology. Tautology. Okay. Okay. So let's come to the fourth problem. So over here we have express the system specifications, express the system specification using the propositions. So we have three propositions over here: P, Q, and R. So P says that the user enters a valid password. Q says access is granted, and finally the statement R is the user has paid the subscription fee. Okay. So now there are three statements over here: A, B, and C. So A says that the user has paid the subscription fee. So this user has paid the subscription fee. This is the proposition R, but does not have a valid password. So having a valid password, that was the proposition P. So over here does not have a valid password. This means the negation of P. Now we have R and P, and what is but over here? But is nothing but the conjunction operation. So this A is nothing but R conjunction negation of P. Okay. The second one is that access is granted. So access is granted is nothing but our proposition Q over here. Okay, so this is Q. Whenever the user has paid the subscription fee. So the user has paid the subscription fee is basically the proposition R over here, and enters a valid password. So enters a valid password, that is our proposition P. So it says that Q, whenever R and P. So Q happens whenever R and P both happens. Sorry, enters a valid password and user, yes. So R and P both happens. So that means that when R and P, that means this R conjunction and P, this happens, then Q happens. So this is a sufficient condition for Q. So we can write it like this. R conjunction P implies Q. So this is statement B. And finally, we have if a user has not entered a valid password. So user enters a valid password, that was our proposition P. So over here, this should be not user does not enter a valid password, but has paid the subscription fee. So paying the subscription fee, that was our proposition R. then access is granted. So access is granted to P. So not P but R, then Q. So but is nothing but our conjunction operation over here. So when both of this is true, then we can both is true, then you should also follow. So therefore, this is our compound proposition C. So we can write A, B, C in terms of P, Q, and R. Okay. Now, the problem 5 is basically checking whether the given statement is consistent or not. So there is a multiple statements that are given over here in A and B. So we have to check whether the statements given in A and the statements given in B are all consistent or not. So let's see first the statement A. So in statement A, we are given that the system is in the multi-user state if and only if the operating system is operating normally. So let's figure out what are the propositions given over here. So first proposition is the system is in multi-user state. So that is our first proposition. So let's name it P. If and only if it is operating normally. So it is operating normally, or the system is operating normally. So this is our second statement, second proposition. Name it Q. If the system is operating normally, so again, this system is operating normally is nothing but our statement Q over here. Okay. The kernel is functioning. So this kernel is functioning. This is a new statement. So we name it as R. The kernel is not functioning in the system. The kernel is not functioning. So that should be nothing but not negation of R. Or the system is in the interrupt mode. So is system is in the interrupt mode. This is the new position. So let's name it S. System is not in the multi-user state. If the system is not in the multi-user state, so multi-user state was P, so this should be negation of P. Then it is in the interrupt mode. So interrupt mode means, and finally the system is not in the interrupt mode. So that is not S. So if we are to write all this, so the final thing, so over here, this is the conclusion that is given. So let's write it in terms of logical connectivities. So it has said that P if and only if Q. So that means P if and only if Q. Now, if the system is operating normally, which is Q, the kernel is functioning. So Q implies R. The kernel is not functioning, or the system is in the interrupt mode. The kernel is not functioning, or the system is in interrupt mode. That means the kernel is not functioning. That was negation R, or the system is in interrupt mode. That is, which is disjunction S. Now, if the system is not multi-user state, then it is in the interrupt mode. So we can write it as negation P implies S. And finally, we have the system not in interrupt mode, that which is nothing but this. Now, if we have to check the consistency of the statements, that means whether all of the statements are true or not. So if we say that this is true, this final statement not is the negation of S is true, then we can say that S should be assigned the value, should have the truth value T. So if S have the truth value over here T, oh sorry, if this is true, then S must have the truth value S. Only then this negation of S can be true. So if S is false over here, then the hypothesis, if over here is a conclusion, S over here is the conclusion, and the conclusion has the truth value F, then the hypothesis must be uh, it must be F, because if it is true, then this uh, this proposition over here would have the value would have the truth assignment false, and therefore to make sure that this truth assignment, the truth assignment of this proposition is true, we must have negation P as false, since S over here is false. So that implies that P must have the truth assignment T. Now again, over here, S had the truth assignment F over here. S had the truth assignment F over here. Now whatever, now if we want to make sure that this proposition must have the truth assignment T, then this literal, not R, sorry, negation of R. So that should have the truth assignment T, because this is a disjunction. So at least one of the literal must have the truth assignment T. So over here, negation of R, that must have the truth assignment T. So that implies that R is nothing but have the truth assignment false. So again, if R have the truth assignment false over here, to make sure that this proposition have the truth assignment T, we have to make sure that Q, that is the hypothesis over here, must have the truth assignment F. Now finally, in the first proposition, we have P by implication Q. So in by implication, that we know that both of these literals must have the same truth assignment. So if Q have the truth assignment F over here, then P also must have the truth assignment F. Now P have the truth assignment F. From here we have found that P have the truth assignment F, and from here we have found that the P have the truth assignment T. So this is a contradiction, because these are this P is a proposition. So a proposition may not have both truth and the false value simultaneously, and therefore this is a contradiction. That means all these statements may not have the truth assignment simultaneously. That is, this system of this system specification that is given in A, this is not consistent. Okay. Now let's go to this B over here. Now for B, we have the router can send packets to an A system. So this is the first proposition. We name it B. Only if it supports the new address space. So this is the second proposition. We name it Q. For the router to support the new address space, so it supports the new address space that was already given in a proposition assigned to a propositional variable Q. So router to support the new address space, so that is nothing but Q. It is necessary. It is necessary the latest software releases to be installed. So this is again a new proposition. So we name it S. The router can send packets to its system. So this was already assigned the propositional variable to the proposition variable B. So this is again B. If latest software is installed. So that is S. The router does not support the new address space. And finally, we have negation of Q. So it says that the router can, so P only if Q. First statement was that P only if Q. Second statement was that for Q, it is necessary it is necessary. The S is necessary. So S is necessary for Q. The third statement was the router can send packets to the edge system if latest software is installed. That means if S, then P. So if S, then P. And finally, the router does not support the new address bus, which is nothing but the negation of S. Sorry, negation of Q. Negation of Q. Okay, so P only if Q. So P only if Q means that only when Q is occurring, then only when Q is occurring, then P happens. So this is nothing but P implies Q, because Q is a necessary condition for Q, not the other way around. Now over here, S is necessary to Q. So S is necessary to Q means Q implies S. So S is the necessary condition over here, not Q. And if S, then P. It is when that is if S, then P. And finally, we have negation of Q. So let's check whether this consistent or not. So for consistency, all of the statements, all of these propositions must have truth assignment. So if this negation Q, this have the truth assignment T, then Q must have the truth assignment F. If Q have the truth assignment F, then from here we can say that whatever the hypothesis is, that must have also have the truth assignment F. Since this proposition over here has the truth assignment T. So therefore, we can say that P have the truth assignment F. Then again, if P have the assignment F, so that means that the hypothesis over here, which is S, this S must have the truth assignment F. In this, by similar logic, we can say that over here, this hypothesis over here, the hypothesis over here is Q. So Q must also have the truth assignment F. So now we can see that all of these systems, all of these statements are consistent. If we consider all of these propositions as true, then we do have a valid truth assignment, which is P is equals to F, Q is equals to F, S is equals to F, P, Q, and S. Okay. Yes. So P, Q, and S, all have the assignment. Then say proposition. So we make sure that all this to the problem 6. So in problem 6, verify whether this when all these statements are logically correct. So let's get around in the first statement. First is given by so verify whether two statements are true or not. So we just start finding each statement, and they both should have the same expressions. Fine. So let's start simplifying this. So we get rid of implications. So you know that if So that is equivalent equivalent to the proposition over here. Of this function. So we will replace this implications with that. So over here we have and you use because both cases this function are common. So we can use the distributed property to make it like this. Now, using Morgan's, we can now write what is the De Morgan's law? De Morgan's law the negative to negative and again the disjunction is by De Morgan's law, then this is nothing but over again now disjunction again but the so implication is like PR is nothing but implied. So we can this variable s, so we can write as so that we have with this proposition. So we can say that these two are equivalent. It is equivalent. These two propositions are equivalent. So the second, so for the second one, we have implies are this statements and make both I mean resolve the same equation. But to prove that they are not equivalent, what can we do? We go to get truth and they so here we will prove that these two statements are logically equivalent. So we just use or I mean you are of them give the truth assignment. All of them are truth assignment. So both of them are false. So the hypothesis for the confusion that should truth assignment that should have the again. So this is nothing but price. Now the hypothesis is true, but the confusion R over here it has the truth assignment. This cannot. It is not. So this should have truth assignment F. So for implies must have the truth assignment F. Now over here we have P implied is basically the truth assignment. So F implies both have the truth assignment F. So that should have truth assignment. Now P is P. Now how is maybe true. The conclusion is true. Then we can what is the truth assignment? This is have the see implies R. This happens for the same truth assignment of P, Q, and R, these literals, we have two positions over here that have different truth assignment for each of these cases. So these have false truth assignment and these have true. So that means they cannot be logically equivalent. So for them to be logically equivalent, for any truth assignment of these literals, they must always have the same truth assignment for each of these cases. And since we have given an example for one case where these truth assignment are not same, so they are not logically equivalent. So E is not logically equivalent. Now, what about C? In C, we have P implies R and implies R, Q implies R. So we have to verify whether these two are logically equivalent or not. So let's try with this one. So we can write it like this. Since P implies Q, that means that this is logically equivalent to not P, disjunction Q. So we can write it like this. And from De Morgan's law, we can simplify this part as this. The conjunction becomes the disjunction. And the literals P and Q, we can write it as literals negation P and negation Q. And finally, we have disjunction R. Now we can use the distributive property over here. That means we can distribute this disjunction over this conjunction, and then we can get now again from this equivalence relation, we can say that this is nothing but P implies Q. Sorry, P implies R. Disjunction is a conjunction. Q implies R. So this is, oh sorry. Okay. Okay, so it turns out to be like this. So what about this one? Okay, so let's try this one. Q implies R, so we can write it as so. This is to disjunction R. So over here, this R and R, the disjunction of R and R, we can write it as R. And that is what we have written over here. Now we can simplify this as negation of this. So this is nothing but P. Okay. So these are not actually equivalent. Okay, so we must have some example for a truth assignment for P, Q, and R such that they are not same. Okay, so what should be the assignment for P, Q, and R? Okay, so let's say that P, Q, and R. Q, and R. So let's say this is R is false, P is true, and Q is also true. No, Q is false. So then PQ implies R. So this over here, P disjunction Q, it must have the truth assignment T, and R have the truth assignment false. So then P implies F. Uh, that means the hypothesis is true, but the conclusion is false. So this proposition must have the truth assignment F false. Now over here, P implies R, disjunction Q implies R. So P implies R, so that should be true. P implies R is false. That again, and this is false, implies false. Now P implies false. This is again similar to this. This should be false, and this must have the truth assignment T, since both of them are false over here. Now, since this is the disjunction between a false and truth assignment, so this must have the truth assignment T. We have one truth assignment for PQR such that one statement over here has the truth assignment F, and the other statement have the truth assignment T. So they are not, again, they are not logically equivalent. And finally, we have the question C, which is P implies Q implies R implies S. And the other statement is P implies R and Q and S. P implies R, that implies Q implies S. Okay. So we have to verify whether these two statements are again logically equivalent or not. So for this case, again, we will try to find a truth assignment to to prove that these are indeed not logically equivalent. So let's give a truth assignment. False, false, true, and false. Now, let's check out this first proposition, which is P implies Q, R implies S. Now, P implies Q, this, so as you can see, that both P and Q have the truth assignment F. So therefore, P implies Q must have the truth assignment T, and over here, R implies S. So since R is true and S is false, that is, the hypothesis is true, but the conclusion is false. So this must have the truth assignment F. Now again, the truth assignment over here, truth. So the conclusion is false, but the hypothesis is true. So therefore, this must also have the truth assignment false. Sir, is there anyone talking? Hello. Okay. So anyway, so the truth assignment for this proposition over here, we have the false truth assignment for this truth assignment of PQ and RS, this intervals. So now let's check out this second proposition. P implies R implies Q implies S. So this P implies R. So since P and R, so P have the truth assignment F and R has the truth assignment true. So therefore, this must be like this. So it doesn't matter whether the hypothesis is true or false, since the conclusion is already true. So we can always say that this truth assignment must, so this must have the truth assignment T. Now over here we have Q and S. So both Q and S we can see they are false. So both hypothesis and the conclusion, they are both false. So therefore this also must have the truth assignment T. Now T implies C. So both hypothesis and the conclusion is true. So therefore this proposition finally have the truth assignment T. So again, for this case, we have shown that there is a truth assignment to this literals PQR and S, such that the first proposition over here has the truth assignment F, and the second proposition has the truth assignment T. Therefore, they are not logically equivalent. So let's go to the problem 7. So problem 7 starts with the dual of a compound proposition. So what is the dual? The definition of dual. So suppose we have a compound proposition like this. So P, Q, okay, let's write it in CNF form. So P, Q, and R, that is R is something like this. So this is a compound proposition. Now, what is the dual of this proposition? So the dual is, okay, so instead of S, let's assign it a constant value like T. So the dual is that if any disjunction, so basically just find the literals will not change. Literal will stay. Only thing is that given any, so also put the brackets over here. So given any disjunction, we replace with conjunctions. Any conjunctions we replace with disjunctions. And also, if there is a constant T assignment, constant T, then we write and vice versa. If there is constant, then we T. Compound, sorry, composition C, and this do this composition. So this is the about proposition. Now, I have given the example, we have do all of this example in the previous example. Later, then change the change the first one. Write Q dot, and so the distances are with conjunctions, and conjunctions are with distances. So is the conjunction, so we similarly into disjunction is to all of this third. So like this P. And it's not conjunction to F. Therefore, those are not this only this like is equals to the negation of P. We can say that this is negation of only these cases we can say that S is equals to star. But if it is a compound like this, you are like this. Then if we try to find the of this is C star would actually be you are so this all the conjunctions are replaced with disjunction, disjunctions will be replaced with conjunctions, and also the are repeated. So all in compound cases we cannot really say that C is equals to C star. So only these the where C equals to star is possible. So the compound statement, compound proposition. Uh, so now I show that the dual is indeed this. If we find and then we find the dual is so this is true. I mean, it's easy to because what dual does is that given any disjunction, it changes to conjunction, and given any conjunction, it is the disjunction, and given disjunction is replaced with a conjunction. And also in a true assignment will be and else is with the truth. Now if we this position here. So this is this is replaced with disjunction, and so basically after two times we have the transformation, but I think transformation means that if you find the that will give the position itself. Okay. Now, as an example, we can see we can find the dual of this C star again. So the dual of C star, this should be like this: E, U, R. This should be conjunction. This is and so this is nothing but the C. Now, finally, we have D. So in D, we have to show that equivalent compound proposition are also equivalent. Whereas compound operator that we have two propositions like this, and these are same. We have two of this. Let's say that let's see an example. Okay, so let's start with a previous example like this. Okay, not okay, basically P is equal. Then we say that negation of P is negation of Q. Because if any assignment on P is equivalent to, that means that any so if P has the set of literals on, so let's say that the list of literals for P is x of 2 xn, and for Q it is x1 to x. So if we give a truth assignment to all this literal, some truth assignment is, and truth assignment for Q over here, they in the same truth assignment, true or false. But both P and Q must have either both are true or both are false. So if for the truth assignment, I think the negative must have false. And since P has attained the value T and P and Q are logically equivalent, and Q must have the attained the value T over here. So negation it must have the value of F over here. We can say that if P and Q are logically equivalent, we can say that the negation of this proposition that should also logically equivalent. Now, what is that? If, any like, okay, so we have a proposition like this. So what the negation is? So if we apply negation, what would happen is that it would change each of these literals to negation P, Q, and the so if you use the De Morgan's law, it happens like this. You can change it like this. If we have this here, from it to negation P, and all the literals negation P is to P, and all the is going to transform into conjunctions. And similarly, if there are any constant assignments like P and Q, so those are also transformed into F and P like this. So this is not this something that we're doing Google or something, but rather we're just using this De Morgan's to convert all this to convert it. All of these are property. All of these are that we the dual partition. Can we move this? That means can we just this again? And we can say that apply again to the literals. Is that after doing this, we have P transformed into this and P is transformed into P. All for all literals, not for this only P, but for all literals. So let's so this is small P. This is not all literals. We have this now. The literals are nothing but variables to save the propositions. Right? So we can say that this so for each of these propositions over here, we can say this is now saved in a proposition like a variable. This is saved in negation S, because if negation P is P plus negation S. Okay, so this is nothing but a these literals are nothing but variables, right? We can write it like this, and instead of using S, we can use P. Then that I mean this is not implications. basically we are assigning so basically so or assigning this literal assigning this literals to another literal. So computing this, if replace each of the literals p negation p to p and p to negation this statements over here. So let negation p turns into some p dash and negation q is turns into q dash after this transformation over here. Then p dash and q dash they will shift to p value. And this p dash and q dash is nothing but p star and q star. That is the dual of this p and q. So this should also be p value. And later we will see that proposition can be written as written with these operators, these three operators over here. So okay, so logical operators is called functionally complete. If every compound proposition involving only this logical operators. That any if we can find any logical operator sorry compound proposition like C can be written as C can be written as all the literals x1, x2, xn, and only these operations. C can be written as an equivalent form that involves only these operators. Literals can say that set of operators. This operators. So what three options here. So three are any proposition that involves only the problem, but if there are positions of these operations, but rather we have something like this as u or p 5. So can we write these in terms of this three operations? We know that p plus q is nothing but negative p disjunction. So definitely we can write this p plus q as negation. Sorry, as negation disjunction. So this one. So what about this one? So this is nothing but implies conjunction implies can be written as this and implies can be written for negation, negation, disjunction, and conjunction. These three operators, we can take any operation like this by implication or implications or something like that. So we can take any operations like that, and we can write it in form of this operation. We can say that these three operations are functional. So what about only negation and disjunction? So if we only have these two operations, then what about P implies Q? So we know that P implies Q, we can write it as only these two approaches. So no problem with that. And what about implications? For application, we have plus Q. Function Q plus P. Okay. So, for conjunction, write it as because we know that negation of negation is that gives the proposition only. Okay. So from here we can write this, and this using De Morgan's law, write it as negation of negation P conjunction. I've written this conjunction using only disjunction and so now over here it only involves operation implication conjunction. This implication operation in this can be replaced like this, and again the conjunction operation can also. Yes, we can say that this set of operations, integration and disjunction, this is complete, functionally complete. Okay. Now, for the third one, we have division operation and so now any disjunction operation like this can be written as using the De Morgan's law. We can write this. Any elimination operation is nothing but this. So this disjunction again is using the formula P disjunction with this. So this is possible writing from with the operators negation and conjunction. And again, by implication, basically a compound proposition that involves the operations implication and conjunction. Yes. So the implication operation can be represented disjunction operation inside the after therefore we can say possible to write therefore this is also functional computer. So we have some compounds over here. And that check so start with this first one. This is given by negation P, negation Q, negation R. P, Q, and S. Reference. And this P, Q, R, negation of So first, we have PQR is literals over here, and this negation is those are over there, but okay. So make sure to satisfy this problem, you have to make sure have a truth assignment, because these are the conjunctions between all these clauses. So each of these clauses must have truth assignment. Then only you can say that this is satisfiable. Okay, so and each of these clauses are basically the disjunction of some literals. So any one of the literal, so if any one of the literal is assigned a true value, then we can say that that clause, that particular clause, have the truth assignment. Okay. So let's say that we assign a value false to R. So if we assigned a value false to R, then we can say that this negation R over here, these are these are the true values. So that means we can say that these are true values. These two clauses already got the true values. Now, if R over here has assigned the value false, then over here we have the R value is false over here. So either negation P or negation Q, they has to be true. Okay. So let's say that we assign a false value to P. If you assign a false value to P, that means this negation P over here and negation P over here, both of them are true. So then these two clauses will have the truths. Now, if P is false, then this P over here, it has the assignment false. It has to negation so sign to true. So it doesn't matter whether over here we have true or false. But at least other clauses have already been assigned a true value. So therefore, those clauses we have. Over here, if we have truth assignment that this, that means we'll have the true value. It doesn't matter what we assign true or we have assigned a true value to S. This is now a truth assignment to RNS. This here. So this is satisfied. So A is satisfied. So what about how many literals are it? There are 4 literals. Okay, 4 literals and 1, 2, 3, 4, 5, 6, 7, 8. 8 main clauses. So now let's say that we assign a value P to the literal P. So if we assign T value to the literal P, then P here, over here, and so over here. These 3 clauses definitely have the sign. These 3 clauses will take the true assignment P. Now, over here we have negation P and negation P, negation P and negation P. 4 negation P's over here. So either R or S over here has to be given the value true. So let's say we take S, we give the truth assignment T to S. So then S over here is true, S over here is true. But and over here, these two, negation of S, they will have the truth assignment F for these two clauses. Now, for this clause over here, both this negation P and negation S, they have the truth assignment F. So to make that this clause will have T and have the truth assignment, we must give the truth assignment true. And similarly for this one, R must negation of R must be true. That means this R must be false over here. So if we do that, negation of R would be true. Over here also negation of R would be true. And over here would be true. We ignore all these errors. Then we can see that for the first clause, we have at least one truth assignment. So first clause will have the truth assignment P. Second clause, again, we have at least one truth assignment. Fourth, fifth, sixth, seventh. So only one literal which have the truth assignment. So given this truth assignment to P, Q, R, and A, we can ensure that this proposition B is satisfied. I mean, the proposition B takes the value, it takes the truth assignment B. So therefore, this is satisfiable. And then we have a question that explains how an algorithm for determining whether a compound proposition is satisfiable or not can be used to determine whether the compound proposition is tautology. So what is the condition that a compound statement C is tautology? So C is tautology and only if we can say that not C is not satisfiable. That means if T is tautology, then any truth assignment to the literals of C, we can say that C is always true. So if C is tautology, so let's prove this statement over here. If C is tautology, then we can say that any truth assignment to the literals of this proposition C will give C to be true. C will have the value true. C have truth assignment T. So C will have a truth assignment T for any truth assignment to the literals. So therefore, not C will always have the truth assignment F. So what does that mean? That not C have always the truth assignment F for any truth assignment to the literals. So that means not C is unsatisfiable. That is not C cannot be satisfied. So that is the first implication. That means C's tautology implies that not C is not satisfiable. So what about the other way around? That means if we say that not C is unsatisfiable, then we have to prove that C is tautology. So we can put this as in a contrapositive manner. That is, we assume that, so basically, so say that this is our proposition P and this is our proposition Q. And what we have to prove is plus Q. This is enough to prove not P implies not P. So this is the contrapositive statement of to the P. So it's enough to prove this proposition. So that means we have to prove that C is not a topology. Then not C is satisfiable. That is what we have to prove. So what does it mean that C is not a tautology? So C is not a tautology means that there exists at least one truth assignment. With the literals of this proposition C such that C is false. I mean, C takes the value false. Such that C takes the truth assignment. So there exists at least one truth assignment such that C takes the truth assignment false. So that means that there exists at least one truth assignment such that is not C takes the truth assignment P. And if we say that there exists at least one truth assignment such that is not C takes the truth assignment, so that means that C is satisfiable. So that was the definition of being satisfiable. So given at least one truth assignment which gives the truth assignment T. So that means this is true. So we have proved that if C is tautology, then so that is possible if and only if not C is not satisfiable. So suppose that we have an algorithm that can solve the SAT problem. So what was the SAT problem? We are given a literal over here as an input, and as an output, it would either give 0 or 1. So 0 means not satisfiable. 1 means it is satisfiable. So this is our algorithm that we already have. Now, using this algorithm, we have to decide whether a given proposition is tautology or not. So this is what we have to build. An algorithm that decide whether a given proposition is tautology or not. So as we have seen in this theorem over here, which says that C is tautology if and only if not C is not satisfiable. So the only thing that we have to use is that using the SAT problem, we have to decide whether this not C is satisfiable or not. So we use this SAT algorithm over here, and given a C over here, we can compute the not C and input this not C to the SAT algorithm. Now SAT algorithm will decide whether this is satisfiable or not. Now, if this is satisfiable, then you can definitely, if this is unsatisfiable, if this not C is unsatisfiable, then we can say that C is indeed a tautology. And if this is satisfiable, then we can say that C is not a tautology. So that means that whatever the output is, if this is not satisfiable, then we say that it is indeed a tautology. That is 0 would go to 1 and 1 would actually go to 0. This means not a tautology, and this means a tautology. So that means whatever the output of the SAT problem should be, we should negate it, and then that negative should be output of the this algorithm tautology. to decide whether it is valid or not. So this is how we can use this algorithm to solve the SAT problem to decide whether a proposition is valid or not. Now let's go to the next problem. So now we have to use the rule of inference to show this is the hypothesis imply this conclusion over here. So what are the hypotheses over here? So first hypothesis is that Randy works hard. So let's say this hypothesis Randy works hard. This is our hypothesis P. Okay. Now if Randy works hard, then he is dull. So let's say that this B is a dull boy. This is basically Q. So then if Randy works hard, he is a dull boy. So P implies Q is given over here. Now third hypothesis is given as if Randy is a dull boy, then he will not get the job. So getting the job, so not getting the job, let's say this not getting the job, will not get this job, the job is basically R. So then this is basically P implies R. And that is the conclusion. Now let's check whether it's true or not using the rule of inference. And in the rule of inference, first we have P, and secondly we have P implies Q. Now using these two statements, we can say, using modest ponens, we can say is Q. Now we have Q, and next we have we include this statement over here. Oh, sorry. Over here we have the Randy. If Randy is a dull boy, then this is true. So therefore it should be Q implies R. Okay. So we have Q over here, and we also include this statement over here. Q implies R. And again, using modest ponens, we can include R over here. And this is nothing but the conclusion over here. So this is true. I mean, these hypotheses indeed, the set of hypotheses over here, this indeed concludes this conclusion R over here. So this is using the set, rule of inference, we can verify that. Okay. So now we have to use the resolution, the rule of resolution, to show that the A and B, both of these hypotheses conclude, we imply the conclusion over here or not. Okay. So for this, for the case A, we have Alan is a bad boy and Hillary is a good girl, or Hillary is a good girl. So Alan is a bad boy. This is the proposition P. And Hillary is a good girl. This is the R proposition Q. Now, Alan is a good boy. It's basically, okay, so we have P or Q. So or is nothing but the disjunction operation. Now, Alan is a good boy is nothing but the negation of the statement P that was given over here. Or David is happy. So David is happy is now a new statement. So we'll name it as R. So is good boy or David is happy. So that is disjunction R. So this implies the conclusion Hillary is a good girl or David is happy. So Hillary is a good girl was Q, or David is happy. So or David is happy is basically Q disjunction of R. Okay, so we have to prove this using the resolution, the method of resolution. So what was the method of resolution? So in the method of resolution, we have seen that if using this statement, so we can, I mean, you have to build a resolution T. and then we have to use using the resolution rules. So using the resolution rule, we have to. So basically, this was the rule. This is the resolution rule. That means if we are given like something like this, P or Q, and not P or not R, we can basically eliminate this and conclude this. So this was the rule of resolution. But anyway, the method was like if we first built a resolution. So each of these clauses. So these are basically clauses. Okay. So this is one clause, and the another clause goes over here. So we built a resolution tree, and the resolution that should be this conclusion over here. Now, if we eliminate this P and not negation P over here, then we can get this over here. So this is one of the results of this hypothesis over here. So therefore, this is we can say that this conclusion is correct. Now, another method is so let's solve the second one, and we will use another method of proving this or verifying this kind of statements using resolution. Okay, so it is not raining, or UFO has his umbrella. So it's not. Let's say that your statement it is not raining. And use the statement that UFO has umbrella. Now, UFO does not have his umbrella. That would be and that was designed already, and or he does not get wet. Okay. So R say that UFO does not get wet. It is raining, or UFO does not get wet. Okay. R, P and R already assigned, and final conclusion is that UFO does not get wet. Okay. So the first statement says that it is not raining, and UFO it is not raining, or UFO gets his umbrella. So P disjunction. The second is that UFO does not get wet. It is R, or P. Oh, sorry. UFO does not have his umbrella, or he does not get wet. So UFO does not have his umbrella, so that should be not a Q. Or it doesn't get wet. That should be this. And the third hypothesis is so which is negation P, or does not, or what doesn't get wet. And this is the final equation as UFO does not get wet. UFO does not get wet, which is R. So to okay, so this by the rule of resolution we can verify this, and this is true when all these hypotheses and the negation of the conclusion. I mean the conjunction of all this. So if this is our hypothesis 1, so this says P1, P2, P3, just name it, and this is our conclusion C. So we can say that this is true when P1 conjunction P2 conjunction P3 conjunction negation of C. This is not satisfied. So by proving this, we can also use the to prove this. We can also use the rule of resolution. So how do we do that? So we have all these. The first hypothesis over here, the second hypothesis over here, The third hypothesis is over here, and finally negation of alpha. So our target is to find at least one false assignment. So how can we do that? So let's say that we have P over here, and we take first we take this two over here. So okay, so instead of that, we can just go for these two over here. Okay. So, this two over here. We can get rid of this P and negation P, and we can get Q R. If I take two values over here, then Q and not P, we can get rid of this Q and negation Q, and we will get R, R, R disjunction R, which is nothing but R. Now R and negation R, that gives us the false sign. So that means by the rules of resolution, we have proved that this is indeed true, because the conjunction, the conjunction of all the hypothesis and negation conclusion, that actually gives us the false assignment. That is basically. So we have and we have the rule of that is not satisfied. So whenever we are given a statement like this, and we have to this is not satisfied, we can use the rules of resolution. This like this. Okay. So these are all the clauses. Now, to make, to prove that this is not satisfiable, we have to, using that resolution tree, we have to find a false assignment, basically. So by combining these two, we can make sure that this is, so basically this should be Q, Q, Q disjunction Q, which is nothing but Q. Okay, so now Q and this. So now over here, we can again get rid of this P and negation P, and which gives us negation Q. Negation Q, and we try to conjunct when we have the conjunction of this Q and negation Q, that actually gives us false. Okay. So still combining to the so conjunction of this over here, and similarly here the conjunction should remove this P negation, give us negation Q. And negation of that Q, false sign. We have using the resolution not satisfied. Okay, so these were some of the problems that help you to solve the assignment. So, thank you. We will meet next.
Excuse me, I don't know about others, but like the network was really bad for me. The voice was breaking. Did somebody else face this problem so that I can resolve if it is mine?
I too face the same problem.
Okay. Okay. To sure that doesn't happen. So this is the first time. Okay. So I will do the
Thank you.
but when you face this problem, I mean, in the middle of the speaker or
So the voice was breaking continuously, like it was lagging.
just okay. Okay, I'll take care of it.
Thank you so
Anyway, if you have any problems or any questions, so if you don't have anything, then this is the end of this.